All right, without further ado, our first speaker today will be Max Hubner, who will be telling us about probing Higgs bundles for local G2 manifolds. Take it away, Max.
Great. Yes, thank you for the introduction, and thank you for inviting me to speak, and thank you to Cody and John for putting together the seminar series. So as Cody just said, today I'm talking about how to probe Higgs bundles for local G2 manifolds using A-colored supersymmetric quantum mechanics. This is work done in Oxford, and it appeared on the archive under this number. Great, so I've decided to structure my talk as follows. After a brief introduction and some motivation, I'm going to talk about the particular class of geometries we're going to be interested in today. Then I'm going to discuss the 7-dimensional field theories, these engineer in M theory, and discuss the supersymmetric moduli space and the vacua of the 7-dimensional twisted superangles theory. This will give rise to some Higgs bundles, and these Higgs bundles will encode the 4-dimensional physics and will extract the 4-dimensional physics using this colored supersymmetric quantum mechanics. We'll do so explicitly for abelian Higgs field configurations, and after discussing that, I'll end with a summary and an outlook. So this work is motivated by the success G2 manifolds have had in engineering semi-realistic 4-dimensional physics and M theory. G2 manifolds are 7-dimensional manifolds with holonomy contained in the exceptional group G2. As is by now well known, within these geometries, codimension 4 singularities can be used to engineer non-abelian symmetries, and codimension 7 singularities can be used to construct chiral matter. Given these tools and others, it's fairly interesting to see what kind of theories one can construct and what exactly determines their properties, their symmetries, spectra, and interactions. Before giving the details, let me make a few more important comments. So within the compactification program, local, that is non-compact G2 manifolds, are used to approximate compact geometries near their singular loci and extract the gauge theory degrees of freedom and their dynamics which localize at those singularities. Local G2 manifolds have had great success in analyzing field theory phenomena such as confinement, gauge symmetry enhancement, and domain wall physics, but are unfortunately less well understood than Calabi-Yau manifolds, for example. In this talk, we will circumvent most of the mathematical difficulties by working with a Higgs bundle description of the geometry. Higgs bundles, their spectral covers and tools to analyze these were first introduced in F theory, where they helped to make the geometric engineering dictionary precise and guide the constructions of compact geometries with favorable properties. The theme of today's talk will be to also approach local G2 manifolds via their Higgs bundles and using some probe particles extract the 4-dimensional physics from these. So the loose question heading out of this motivation is simply what determines the 4-dimensional physics engineered by local G2 manifolds in theory. So G2 manifolds. Sorry, Cody, my screen froze on one of my devices. Did it freeze on yours?
I think on my end, there was a momentary freeze and you cut out a little bit, but you are back now.
Okay, wonderful. Then I'll just take right off here. So the class of geometries we'll be interested in are these ALE fibered G2 manifolds. So there are 7-dimensional spaces fibered by ALE spaces over a compact base M3, which is in total space as a supersymmetric cycle. Each of these fibers contains a bunch of 2 spheres, sigma I, and each of these fibers is hyperkähler, with a hyperkähler triplet denoted by omega 1, 2, and 3. All of this geometric information can be packaged into the Higgs field. The Cartan components of the Higgs field are 1 forms on the space M3, and their functions record the symplectic volumes of these two spheres with respect to the hyperkähler triplet. So whenever one of these forms develops a zero, the corresponding two cycle in the fiber above collapses and the singularity enhances.
Hey, Max, let me interrupt just for a second. The connection is a little bit rough. I'm not sure to help, but maybe try turning off your video.
I will give it a shot.
Why not?
Stop. Okay. Right. So there are these Higgs fields. They have zeros, and whenever the Higgs field has a zero, the singularity in the geometry enhances because the two cycle collapses. We'll assume that this happens at isolated points on the base manifold. Another job of these two cycles is that they trace out supersymmetric three cycles. So here on the left, I've drawn a supersymmetric three sphere, which is traced out by a single such two sphere. This two sphere collapses in two fibers above two distinct points of the base. On the right-hand side, I've drawn another supersymmetric three sphere, traced out by three linearly dependent two spheres, sigma, I, j, k, which each collapse above three distinct points of the base. Projecting these three spheres, well, to M3, one finds lines and a Y-shaped tree which connects the loci where the singularities enhance. In M theory, these three cycles, these three spheres can be wrapped by M2-branes, and these generate the superpotential down in 4 dimensions. The main part of the talk will be about understanding these contributions, in particular addressing following three questions. What is the global structure of the network of supersymmetric three spheres and the M2-brane instantons? What do the M2-branes wrapped on the supersymmetric three spheres descend to in an effective 7-dimensional field theory description? And how can their contributions to the 4-dimensional superpotential be computed from the 7D field theory description? So, of course, I'm standing on the shoulders of giants here. So these questions have been asked in various contexts and in different ways before. So let me take a step back and put my research into context with past results. So here is a minimal sketch of the theories involved and a very incomplete list of references. At the top, we have M theory on this local G2 manifold, X7. And reducing along the ALE fibers, one finds a twisted 7-dimensional superangles theory on M3. Compactifying on M3, one finds the 4-dimensional field theory we are interested in. It was at the beginning of this century, Achaya and Witten were the first to notice that the supersymmetric three spheres I just showed you are relevant in determining the superpotential in 4 dimensions. The M2-branes on these instantons, their effects to the contributions to the superpotential were first computed for individual instantons by Harvey and Moore in their 1999 paper, directly in M theory. An alternative way of computing these instanton effects is to do so directly in the twisted 7-dimensional superangles description. And here it was Pantev and Weinhold that first noticed a relationship between Morse theory, supersymmetric quantum mechanics, and these M2-brane instantons. This allowed them to compute mass terms for geometries characterized by a Higgs field with a fully reducible spectral cover. But, and then subsequently, Andreas, Sebastian, myself, and Sakura extended this setup to a more spot configuration. But it remained unclear how to handle more general geometries and how to approach higher point interactions in this formalism. And this is exactly what the research I'm presenting today is going to be about. Namely, in this work, I introduce colored supersymmetric quantum mechanics, which is all the information in this compactification, including non-perturbative effects in correspondence with all M2-brane instantons. But before telling you about this, I need to tell you a bit more about this 7-dimensional super Yang-Mills theory. So fine, where does this come from? So M theorem, this local G2 manifold X7, gives, after reduction along the ALE fibers, a partially twisted super Yang-Mills theory on M3. The scalars along M3 are twisted into a one form, which is the Higgs field, and this complexifies with the connection along M3 into this complex Lie algebra valued one form phi. The supersymmetric vacua of this 7D theory are now solutions to the system, which I've wrote out here, where Fa is the curvature of the connection along M3. When this curvature is non-vanishing, we call the solution flat, and it's T-brane-like. And if the curvature vanishes, then the Higgs fields commute, and we refer to the configuration as abelian. Given such a vacuum configuration, the four-dimensional physics is completely determined, and it follows by dimensional reduction, or well, compactification rather, on M3. For this, we need to determine the zero modes along M3, and these follow from the Laplacian H, which is derived from this exterior derivative twisted by this complex one form phi. The equation I just showed you state that Q is nilpotent, and so the zero modes are counted by these cohomology groups here. There's an alternative way of counting zero modes and the problem, and that is one studies perturbative zero modes and non-perturbative effects. Perturbative zero modes are Lie algebra valued one forms, chi-A, which are sharply localized at the zeros of the Higgs field. And they are in correspondence with codimension 7 singularities in the ALE geometry. To derive the true zero modes, then, one needs to compute this mass matrix here, and which is given by an overlap integral as shown here, and then compute the kernel of this mass matrix. Finally, the 7-dimensional theory also gives an expression for the Yukawa couplings down in 4 dimensions as this triple overlap integral here. And it's at this point that the colored quantum mechanics makes its first appearance. And this is because the colored quantum mechanics will be such that its physical Hilbert space is exactly the field space of the compactification, Lie algebra valued forms, and its supercharge will be exactly this operator which determines the zero modes. So let me tell you about this colored quantum mechanics. So this quantum mechanics is a sigma model into M3, and the dynamical fields are, well, the coordinates xi, I1, 2, 3, and their superpartners psi I, which are sections of the pullback tangent bundle. And then additionally, we have color fermions, lambda alpha, which are valued in the pullback of the gauge bundle. The dynamics of these fields is determined by the Lagrangian as shown here. This features standard kinetic terms for the fields. Then there are interaction terms, which are set by the Higgs field and the connection A on M3. And then there's a Lagrange multiplier term, which deems only those states physical that have a single lambda bar excitation in the lambda bar Fock space. Canonical quantization of this SQM then gives this Hilbert space, Lie algebra valued forms on M3, and this supercharge. So here is the field content again, and the picture I would like you to keep in mind. So the image that one should have is that of a particle moving around in M3. And to that particle, there are two vectors attached. One is the psi vector, which details the fermionic bosonic content of the particle. Another one is the lambda vector, which carries information on how the particle sits in the Lie algebra. Given both of these vectors, one can then derive from the Higgs field the potential that the particle moves in. Very good. So I just argued that we can analyze the zero modes in the compactification of the 7D super Yang-Mills theory by having a look at the ground states of this quantum mechanics. And so we're interested in analyzing the perturbative ground states and the instantons of this quantum mechanics. So the starting point here is the supercharge Q, which is written out here before it's quantized. Perturbative ground states are then given by constant maps, which are annihilated by both the supercharge and its conjugate. So we find that they are labeled by pairs, x and lambda, which are points in M3 and, well, Lie algebra generators in the Lie algebra, such that phi lambda of x vanishes. So one can think of the color vector lambda as specifying a linear combination of two spheres in the ALE geometry, and the points x as telling you where this combination of two spheres collapses. Similarly, half BPS instantons are found to be piecewise solutions to the flow equation. And this flow equation is with respect to this one form phi subscript lambda. And this one form follows from the Higgs field by an appropriate contraction with these color fermions. Additionally, one requires that the parallel transport of the fermion, well, the fermion is parallelly transported along the flow. Here, I've drawn such an example. So this is a 3-valent half BPS instanton, which connects 3 perturbative ground states labeled by A, B, and C. And an interesting fact is that each of these flow trees lifts to a supersymmetric 3-sphere in the ALE geometry, the ones that I showed you before. And so we find this very interesting correspondence between the colored instantons of this quantum mechanical system and the 3-spheres, and therefore the Euclidean M2-brane instantons in M theory. So I would like to make this more precise, and for this we will have a look at specific configurations, namely geometries which are described by abelian Higgs backgrounds with fully factored spectral covers. So these are solutions to the BPS system I showed you before, which have a trivial connection and a diagonal Higgs field valued in the Cartan subalgebra. So the BPS equations then require that these Cartan components are harmonic, closed and co-closed, up to some source terms that we introduce to make the setup more interesting. And on simply connected manifolds, the Higgs field, so these Cartan components, thus derive from a potential which solves Poisson's equation. We have some restriction on the codimension of the charge loci. So we want to understand the ground state structure of the quantum mechanics probing this setup. And here one starts by first analyzing the one particle sector. The first thing one notices is that the supercharge is diagonal and therefore preserves the color, the Lie algebra generator of a ground state, and similarly so does the Hamiltonian and therefore time propagation. So a particle which is oriented along some direction in the Lie algebra will stay that way. Due to this, the dynamics of the one particle sector splits, and we find following correspondence. For every root in the Lie algebra, within the colored quantum mechanics, there's a copy of Witten's quantum mechanics mapping into M3 with a supercharge determined by the root. The different one particle sectors interact via multi-particle effects, which I want to discuss and which show their face when one tries to compute the Yukawa overlap integral I showed you before. So this is the Yukawa coupling in 4 dimensions. This is the overlap integral that determines it. And the strategy for computing it is to rewrite this in terms of a path integral and then evaluate the path integral using supersymmetric localization. The way that this works is that one expresses each of the perturbative ground states here using this formula, where here psi r is a profile, a wave function profile, highly localized at the site of the perturbative ground state, and then it's projected onto the perturbative ground state by time evolution. Having made this substitution, one can then use the standard methods by Feynman to split up the time intervals, insert identity operators, and transition to the path integral. If one is careful and what one finds is that one doesn't find the path integral over paths, but one finds a path integral over these Y-shaped configurations. So the measure one finds is a set of coordinates for each leg of this Y-shaped tree. And the action which governs the dynamic is the sum of three actions which, well, these actions are defined for each of the legs of the Y-shaped tree. With this setup, one can then apply supersymmetric localization and find this result. And remembering that the component functions of the Higgs field recorded the symplectic volumes of the two spheres in the ALE fiber, one finds that this is nothing but the volume of the supersymmetric 3-sphere. And this exponential suppression factor matches with the results of Harvey and Moore. Great, so one presses on with the analysis and at the very end finds that following effective four-dimensional theory. So first of all, the mathematics which governs the four-dimensional physics is Fukuyama's Morse theory with multiple Morse functions. The metaspectrum is determined by the Morse theory of each of the individual Morse functions and determined to be given by these cohomology groups. They count the chiral and conjugate chiral multiplets. They need not be equal, and the spectrum can therefore be chiral. Yukawa couplings are then effects involving multiple Morse functions and are encoded in a cup product on these cohomology groups with strengths, as I've just shown you. Okay, so this is basically the simplest setup. Let's move on to a slightly more complicated setup. These are geometries characterized again by abelian solutions, but now with not fully factored spectral covers. The solutions to the BPS equations under consideration, again, have a trivial connection. And the Higgs field is now diagonal with one-form eigenvalues lambda k, which are again harmonic up to source terms which we allow. These are now in codimension larger than one sub-loci. Solutions, Higgs field solutions to these equations are distinguished by their spectral cover. So the spectral cover is nothing but the union of the graphs of the eigenvalues in the cotangent bundle, and can have one of two properties. Either the eigenvalues are globally defined, this is the case we discussed before, or the eigenvalues are connected by branch cuts and are not globally defined. This is a setup one often encounters when studying local models for TCS G2 manifolds. So what does the particle see when probing such a Higgs field configuration? So first of all, the local analysis in terms of the perturbative ground states and the instantons remains unchanged because these are inherently local. But there are now new global effects due to the monotony locus, such as color mixing. So whenever one encircles a monotony locus, the eigenvalues of the Higgs field are interchanged according to monotony action. And whenever a particle follows a flow line which follows a flow line of a collection of eigenvalues, it, after encircling the branch cut, seems to follow the flow line of a different collection of eigenvalues. It changes color. However, this is something that the particle itself doesn't experience, and to it seems to be probing an enlarged target space. A target space which is a covering space of M3 and which is topologically a component of the spectral cover. So what one sees is that time evolution does not preserve color, and the splitting of one particle sectors like we had it before needs to be refined, and the refinement is following. One now finds a copy of Witten's SQM for every monotony orbit in the Lie algebra, and this SQM maps into a space which is topologically a component of the spectral cover with a supercharge which follows from a gluing construction. So one again works a bit harder, and then one finds that the effective four-dimensional physics is determined the following. So the gauge symmetry is not determined by the commutant of the Higgs field, but by its stabilizer. Again, the chiral and conjugate chiral multiplets are counted by the first and second of these Novikov cohomology groups. Now, with respect to a different target space and a different Higgs field. And again, the Yukawa couplings are encoded in a cup product on these cohomology groups with the strengths as shown before again. So I'm closing in on my time, so let me give you a summary of this talk and the results of my paper. So in my paper, I introduce a colored supersymmetric quantum mechanics, which can be used to probe these Higgs bundles, which describe and descend from local G2 manifolds. This quantum mechanics contains all the information of the compactification of the 7-dimensional superangles theory. And one can make the non-perturbative effects in this compactification explicit. And because these non-perturbative effects in the 7-dimensional superangles theory originate from M2-brane instantons, we find following correspondence between the Euclidean M2 instantons and the instantons of the colored supersymmetric quantum mechanics. This can be exploited computationally to compute these mass matrices and the Yukawa couplings and make statements about the 4-dimensional physics. So before I end, let me give you an outlook on what is left to be done. So first of all, the quantum mechanics takes a Higgs bundle and then tells you which cohomology groups determine properties of the 4-dimensional physics. It is not useful to engineer such a Higgs bundle, and it is of limited use in computing the cohomology groups. So these are two places where advancement is possible. Then the Higgs field, the color quantum mechanics can be used to not only probe abelian configurations, but any solutions to the BPS equations of the 7-dimensional system. In particular, it would be interesting to see what it has to say about fluxed T-brane solutions, which were first analyzed in this paper here. Then something which is also interesting is to ponder the M-theory origin of this colored quantum mechanics. This is something that Cyril pointed me towards. And going over the computations by Harvey Moore, what the case must be is that this quantum mechanics is in some sort a dimensional reduction of an M2-brane probing a G2 manifold. So fleshing that out would be a valuable contribution. And this would put this approach of probing Higgs bundles on a more general footing and allow it to be extended to other Higgs bundle vacuum, such as those discussed in this reference here. With this, I'd like to conclude and thank you for your attention.
All right, thank you, Max, for the very nice talk. Let's all thank Max with our clap emojis. Are there any questions for Max? Fengjun? Did I say that correctly? Has the first question?
Yeah, thanks. Yeah, I'm not sure I understand correctly. So here you only focus that the 3 cycle left by this M2 instanton being topological being H3.
Yes, but that's part of the geometry. So if you set it up as an ALE vibration, then you only find 3 spheres, and these are the ones which generate the superpotential. But maybe you were asking something else.
Yeah, I'm wondering, for example, if there is some possibility that this topological is like S2 times S1, like it's not an isolated.
So this could happen when these flow lines, for example. So in the very first picture, right, I showed you a 3-sphere which projected onto the base gave a line. If you can find a Higgs field configuration where such a flow line closes in on itself, then you would have a setup where these associative submanifolds would be S1 times S2. But this is excluded in the details of the BPS solutions, which I've considered here.
Okay.
So,
yes.
yeah.
Okay, our next question is from Craig.
Hi, Max.
Hey,
so
Craig.
I have a kind of vague question, but I'm just curious if you can say something about, so the colored super quantum mechanics, is then, at least in some sense, capturing what kind of codimension 7 singularities you can have in G2 manifolds. Is there any
Yes.
way that you sort of start classifying and saying every possible singularity corresponds to some kind of configuration of the superquantum mechanics, and then learning something about the possible codimension 7 singularities geometrically?
I don't think so. So the way that the quantum mechanics works is, as part of its defining data, you give it such a Higgs bundle, and that Higgs bundle will have a Higgs field, and that Higgs field will have zeros. Those zeros are the codimension 7 singularities if they're isolated. So all of this geometric data goes into setting up the quantum mechanics, and then the quantum mechanics is used to study the four-dimensional physics. It could very well be that one can exclude some configuration because it might not make sense or might be ill-defined if you try to apply the quantum mechanics to it, but that's not the way around that the quantum mechanics works, unfortunately. So I'm hesitant to say that it could make progress on that question.
I guess, yeah, okay. I guess the question I was saying was, can you choose, sort of say you want to look up the full set of all possible quantum mechanics with some kind of pole structure? And is there reason to believe they would all correspond to some kind of G2 codimension 7 singularities?
So, I mean, so this is deep mathematical territory now. So what I'm doing here, right, is I'm taking a Higgs field configuration, and that's it. And there is a hope that each of these Higgs field, well, there's a very justified hope that each of these Higgs field configurations lifts to a G2 geometry. This is things that Rodrigo has been working on. And so the question of what singularities can be engineered is, in this with this setup, equivalently stated as, can I write down, and what Higgs field configurations can I write down? And that question already is a little bit simpler, but that's also less well understood. So in the fully factored case, which Sakura and I and Pantev and Weinert have discussed, the only thing you can do is these source loci, and that already completely determines your background. But how one would generate all possible Higgs field configurations and singularities in the more general setup is something I don't know.
I see. Okay, very good. Thank you.
Thank you.
All right, if there are no further questions, let's thank Max one more time.